Hi, hello everyone. Hi, this video I'm going to demonstrate an example to finding the loading function of a beam. Okay, and this problem because the distributed load is a little complicated. Okay, so that's why I want to demonstrate this example. Actually, this example is on page 761, okay, on the textbook. Yeah, very simple. Okay, if there is a beam, okay, placed on the support A, this one A, let me call it maybe I call it here is A, here is B. Okay, A is a roller support and B is a pin support. Okay, and this is the external loading acting on this beam. Okay, so find the loading function and also the shear force function and moment function. Okay, and there is a distributed load acting on this beam, and also there is a concentrated moment acting at this position of the beam. Okay, so for finding the the loading function, we need first of all we need to calculate the reaction force from the support. Okay, reaction force from the support, and in order to calculate reaction force from the support, you need to use the free body diagram and then use the rigid body equilibrium. Okay, so free body diagram. Okay, we just we treat this this beam as a line. Okay, and free surrounding. Okay, and there's a distributed load here, and there's a concentrated moment. Okay, and the next thing we have to calculate reaction force from the support. Okay, so we had to okay, so we already know that okay, because A is a roller support, so there is a reaction force AY, and B is a pin support, so there is a reaction force BY, and here is BX. Okay, and then we have to use the rigid body equilibrium to find the AY, BY, and BX. Okay, but the problem here is, okay, here is a distributed load. Okay, in order to use the rigid body equilibrium to calculate this reaction force, we need to do the simplification on this distributed load. Okay. Okay, and okay, how do we do the simplification of distributed load? Okay, here this shape is a trapezoid. Okay, and for trapezoid, we can see it's a combination of a rectangular and right triangle. So if we draw a line here, okay, you see this distributed load. Okay, this distributed load is equal to a rectangular part plus the right triangle part. Okay, for the rectangular part. Okay, Okay, I call it, okay, we call it FR1. Okay, what's the resultant force? Okay, if we call it FR, okay, 1. Okay, what's the resultant force under this rectangular distributed load? Okay, it's area under the curve, right? So here the height here is 3 kilonewton per meter and length is 3. Okay, don't forget the length here is 3. Okay, so it's 3 times 3. Okay, so it is equal to 9. So it's 9 kilonewton. So it's FR1. The resultant force of this distributed load is 9. Okay, but we have another right triangle distributed load here. Okay, so what's the distributed load for resultant force for this right triangle? Okay, yeah. Okay, here the height is also 3 kilonewton per meter. Okay, because the height is 6 minus 3, so it's 3 kilonewton per meter. The length is also 3. Okay. Okay, here, but I forgot, I should say the direction. The direction is pointing downwards. Okay, we have to notice this. Okay, so what's the resultant force for the triangle, this right triangle distributed load? Okay, it's equal to, don't forget the length here is 3. Okay, it give you the problem already give you the length in this length here, so it's 3. So is 1/2 times 3, so it's a 4.5. Okay, it's kilonewton. And don't forget its direction. Its direction is also pointing down. Okay, and what is position? Okay, what is position? Let me use the maybe use blue one. Okay, what's the position? Oh, it's right. Oh, okay. What is position? What is the position? Okay, of the resultant force. Okay, for the rectangular, it's right at the center of the area. Okay, the center is here. Okay, and we know the length here is 3, right? So what's the distance here? Distance here is 1.5. Okay, and what's the position for the position for the FR1? Okay, don't forget it depends on your coordinate system. If we set the coordinate, origin of the coordinate is here. Okay, we said A point A is the origin is here. Okay, what's the position of the result, the FR1? Okay, here is we already know here is 1.5. Okay, its position is 1.5 here, but don't forget, based on this coordinate system, it's 3 plus 1.5. It's 3 plus 1.5. Okay, so it's 4.5. Okay, what's the distributed load for the FR2? The FR2, I think he's here. Maybe the position is very, very close to here. And we know the distance here is 3. So what's the distance here? The distance here is 1, right? Okay, the centroid of the right triangle. You have to memorize this. Okay, here is 1. Okay, so what's the position? Okay, the distance here is 1. So the position is okay, I think it's 6 minus 1 is equal to 5. Okay, right? Right? Yeah, 5. Let me check. Yeah, it's right. Okay. Okay, if we have this information of this distributed load, simplification of this distributed load. Okay, I'll write another free body diagram. Okay, it's more clear free body diagram. Okay, so same thing. Okay, we have a position A and position B, and the center we have the 1.5 kilonewton times meter. Okay, so let's put the FR1 and FR2 in the free body diagram. FR1, the position is 4.5. So I think maybe it's 4.5. Yeah, I think maybe it's here. Okay, it's 9 kilonewton point down. Okay, and here is 1.5. Okay, and we have another FR2, right? Well, magnitude FR2 is 4.5. 4.5 is here. And what's the distance? Distance, I think here is 2. Okay, because 5, so here is 2. Okay, 2 meter. Okay, here is 1.5 meter. 1.5 meter. And don't forget our reaction force. Okay, AUY. Okay, here BY. Okay, BX. Okay, so okay. Now we use the rigid body equilibrium. Okay, rigid body equilibrium. Equilibrium. Okay, so rigid body equilibrium. Okay, what's the condition for rigid body equilibrium? Still remember? Okay, the condition for rigid body equilibrium. Okay, the net force or resultant force, the resultant force of the whole system must be 0, and the resultant moment of the whole system must be 0. Okay, let's check out the resultant force of the system. Okay, let's check out the resultant force of the system. Okay, we check the x direction. Okay, we only have bx is belong to x direction and x equal to 0. Okay, that doesn't help that much. Okay, but at least we know bx equal to 0. Okay, Okay, the resultant force in the y dimension all must also be 0. Okay, so for this calculation, I define the convention. Okay, where I assume okay point up is positive and counterclockwise is positive. Okay. Okay, let's back on the FRY calculation. AY point up, we assume it's point up. Okay, just assume everything is positive. Okay, AY. Okay, here, okay, this moment we can temporarily ignore it. This moment, okay, when we have 9 kilonewton force point down, so it's 9, it's a negative. And here we have a if resultant force 2, 4.5 kilonewton point down. Okay, so also negative 4.5. Okay, and we have a reaction force By. We assume it's positive. Okay, let's point up. Okay, By is equal to 0. Okay, so from here you will get the Ay plus By is 13.5. Okay, so so we use the resultant force is equal to 0. So another condition for rigid body equilibrium is the resultant moment also must be 0. So for the resultant moment, we also need the reference point. Okay, we set the reference point at A. Okay, so let's see. Okay, how many moment we have. Okay, so first of all, the 1.5 kilonewton times meter, the concentrate moment. Okay, we need to consider it, and it's counterclockwise. It's clockwise. It's clockwise, so it's minus 1.5. Okay. Okay, the AY, the reaction force at point A, this won't create any moment because we set the reference point at A for calculating the moment. Okay. So the other is so we consider other force else. Okay, for the Newton, 9 kilonewton point down, 9 Newton point down. A reference point is A, so it will create a clockwise rotation. Okay, so the force is 9. Well, what's the lever arm? Here is 3. Don't forget the distance here is 3. So 3 plus 1.5, so it's 4.5. It's 4.5, and it's create a clockwise rotation. So it's a negative here. Okay, and another thing is we'll have a 4.5 kilonewton point down. Okay, also 4 point down, a reference point here. So it's also create a clockwise rotation. So 4.5, what's the lever arm? The lever arm is 3 plus 2. Here is 3 and plus 2 here. So it's 5. And it's because clockwise, so it's negative. Okay. So the force at the reaction force at B, okay, because Bx equal to 0, we don't know it. So maybe we can just ignore it. And the By, okay, By is point up, the reference point is A, so it will create a counterclockwise rotation. So it will be positive. So By times what's the lever arm? The lever arm it should be 6. Okay, 3 plus 3 is 6. Okay, and it's it's counterclockwise, so positive and equal to 0. Okay, so from this equation, I think you can solve that. Let me check if my equation is right. Okay, I got this. Yeah, it's right. Okay, so maybe using your calculator, you will find, okay, By is positive 10.75, and unit is kilonewton. And because initially we assume it's positive, and we get a positive answer, so that means it's really positive. Okay, its direction is also point up. Okay, and once you solve the By, okay, you can get the Ay directly. So what's the Ay? Yeah, choose check by self. Ay is 2.75 kilonewton. Okay, and its direction, was initially we assume it's point up, and we get a positive value, so it's really point up. Okay. Okay, so we solve the reaction force under this loading. Okay, so the next step we can write down the distribute distribute load function, and we have to represent this distributed load by discontinuity function. Okay, so the next thing is, okay, how to okay, I think in July maybe I need to cut this one. Okay, copy this one. Okay, and then move it down. Okay, paste. Okay. Okay, so okay, write down the distributed load function or loading function. Okay, so let's write down the loading function. We start from the left. Okay, we start from the left, and also we set origin at O. Okay, we set origin at the position A. Okay, we start from the left. Okay, at the point A, yeah, be careful. In the point A, we have a reaction force. Okay, reaction force AY 2.75 kilonewton point up. So at the position A, we have a concentrated load. Okay, so the concentrated load, if we want to represent the concentrated load by this continuity function, yeah, we know it's at position equal to 0. Okay, so this will break position at 0. Okay, for concentrated load, what is its power? Its power is -1. Don't forget, and its magnitude is 2.75. Okay, it's positive. Okay, so okay, at here position equal to 3. At position equal to 3. Okay, position equal to 3, we have a concentrated load. Okay, for the concentrated moment. Okay, for the moment, if we want to represent the moment by a discontinuity function, what is power? Okay, power is -2. Okay, don't forget it. Okay, so the 1.5 kilonewton times meter, the moment is it's clockwise. Okay, it's clockwise, -1.5. Okay, but I told you, okay, for the moment, so we want the moment we want here is an internal moment. This is an external moment. It's -1.5. It's absolutely right. But right now we want the internal moment. So in order to do that, we need to put the negative sign in front of the moment. Okay. Okay. So it's minus 1.5 times x minus 3, break it to the power -2. Okay, so be careful for this. Okay, be careful for this. Okay, so we solve this concentrated load at the position A and concentrated moment at position for x equal to 3. Next thing we have to deal with this concentrated load. Okay, concentrated load. So here is so I need to draw another graph to explain this problem. So right now we have distributed load, and the shape is like this. Okay, this is distributed load, and here x equal to 3, then is x equal to 6, and 6 is the end. Okay, I will notice the end. Okay, so how to use the how to represent this distributed load by a discontinuity function, and like we do the simplification. Okay, this load, the trapezoid load, we can be decompose it as the combination of the rectangular and a right triangle. rectangular is here. Let's say it's x equal to 3, x2 equal to 6. Okay, draw a line here. Maybe not straight, but yeah, bear with me. Okay, yeah, I don't have a ruler here. Okay, and the other is the right triangle. The right triangle here is also x equal to 3, and this is x equal to 6. And here we have this here is the height here is 3 kilonewton per meter, right? Okay, and 3 kilonewton here per meter. Yeah, this is 3. Yeah, this is 3. This is 3. Don't forget. Okay, this trapezoid can be see the combination of these two shape. Okay, so if we can look at so how to represent these two simple distributed load by a discontinuity function. Okay, for the uniform distributed load, for here. Okay, let me write down for the uniform distributed load. Okay, it starts from x equal to 3. So x equal to 3. And it's end at the x equal to 6. Okay, if you remember for the range for distributed load. Okay, sometimes we have a combination of two discontinuity function. Okay, for the range between 3 and 6, we have to use this representation. Okay, so yeah, let me write it down. Sorry, minus, this is minus 3 here. Okay, for the uniform distributed load, okay, the power is 0. Okay, so so if the complete description for this distributed load is minus 3 bracket x minus 3 power 0 minus 3 bracket x minus 6 to the power 0. Okay, but I say I give a notice before, if this is the end, okay, you can ignore everything at the end. Okay, you can ignore everything at the end, so this part we can ignore it. Okay, right? Okay, so in this problem, this distributed load is equal to this one discontinuity function. Okay, and for distributed load for the right triangle, yeah, it also starts from x equal to 3. So there is a power here. So it's also starts from x equal to 3. So bracket x minus 3. And power, because the linear, so its power is 1. Okay, and here before the discontinuous function, here you need a slope. Okay, you need m. Okay, if you remember the slide. Okay, this is a slope. So how to calculate this slope? Okay, here, don't make things very difficult. The slope, how to calculate slope? Use the definition of slope. It's delta x. It's delta y over delta x. Okay, the delta, we said the reference point is here is 0. So delta y is pointing down. So it's minus 3 minus 0. And the position here is 6 and minus 3. Okay, so the slope will become minus 1. Okay, the slope will become minus 1. So here the slope will be the minus 1. Okay, don't make this thing too complicated. Just a simple definition of slope. Okay, so here we can. So here is the slope. Here is slope. Okay, slope is minus 1. Okay, And for this distributed load, it's all the way to the end, all the way to the end. So in fact, if we want to, in fact, we have to cut it off at x equal to 6. We have to do something at x to equal to 6, because this discontinuity function starts from x equal to 3 and all the way to the infinity, all the way to infinity. So we have to cut it off at x equal to 6. But in this problem, the very lucky here is x equal to 6 is equal. This is x equal to 6 is the end. Okay, everything related at the end we can ignore it. Yeah, for precisely we have to cut it off at equal to 6. So we have to add something for x equal to 6. But since x equal to 6 is the end, so we can ignore everything at the end. So this is just for this problem. For this problem, the right triangle distributed load function is just represented by this simple discontinuity function. Because in this problem x equal to 6 is at the end. So okay, we can ignore everything from the end. Okay, so so the answer is very simple here. But that's for this problem. But sometimes it's not very lucky. If this is not the end, this is not the end, you have to do something. Or you have to do lot of things to cut it off. Okay, so we finish here. So let us write down the total. Okay, and okay, don't forget we also have the reaction force at position B, right? We have By. We have at position B we have By equal something, right? We have By equal to maybe I don't write here. Okay, so we'll have By. What's the value for By? By is 10 point. So we have a reaction force for By is equal to 10.75 and position is up. Okay, yeah, but the same reason, because position B is the end of the system, so you can ignore everything at the end. So we don't consider the concentrated loading at the position B because it's at the end. Okay, so what's the final answer for this problem? So the final answer is Wx equal to 2.75 x minus 0 power minus 1 plus 1.5 x minus 3 and power minus 2, and the distributed load here is minus 3 x minus 3 power 0, and final is minus x minus 3 to the power 1. Okay, so this is the final distributed load function. Let me check. Do I get it right? Yeah, I get it right. Okay, so since you got the distributed load function, okay, so what's the shear force function? Okay, I think it's very easy. Yeah, just use the rule for integration rule for the discontinuity function. Okay, this integration rule for a discontinuity function. Don't forget the power is minus 1, so just add 1 to the power. So okay, minus 0 becomes 0. This is a power minus 2, so just add 1 to the power. X minus 3 power minus 1. Okay. Okay, and here, and power 0, power 1. Yeah, just use the regular integration rule from your calculus. You put a polynomial in the rule for integrating a polynomial function. So it's very simple, and this one will become 1/2 x minus 3 2. Yeah, right. Okay, so that's a shear force function. Okay, next one. Okay, the final important is what's the moment function. Moment function, okay, power 1, this is power 0, so integration rule is also very simple. X minus 0 power 1. And here is power minus 1, don't forget the integration rule, just add 1 to the power. Okay, the power 1, 2, just typical integration rule. So 2 over 3 x minus 3 power 2, and this is 1. My final one is minus 1 over 6 x minus 3 to the power 3. Okay, so this is the final answer for the loading function, shear force function, and moment function for this system. Okay, the lucky thing is in this problem, lots of things happen at the end, and for the end, at the end of system, we can ignore lots of things. Okay, if this distributed load is not at the end of this system, that will cause lots of problem. Okay, you have to yeah, you have to deal with cutoff issue. Okay, I think maybe that's part of your homework. Okay, so just stop the demonstration here. Hope you can understand this problem more. Okay, we'll see you in another video. Bye bye. Hope not too bad.